Hello Comets, and welcome back to another video on physics. My name is Alex S, and today we'll be exploring the relationship between calculus and physics. And so there's a few different topics that we can do this with, and the first will be position, velocity, and acceleration. So here we have a magnificently drawn car, might I add, that is going in a certain direction, and we've mapped out the velocity over time. You see we have this velocity function here. And so the question says to find acceleration over time, so that function, the position over time, so that's another function, and then the total change in x if, of course, we start at the origin. And the time period we're discussing here is from t is equal to 0 to t is equal to 6. So how do we relate position, velocity, and acceleration? Well, we do know that velocity is equal to the change in x over change in time, and we know that acceleration is equal to the change in velocity over the change in time. And so if we do the calculus variance of this, this goes to dx over dt, and this goes to dv over dt. So acceleration would be the easiest to figure out here. So acceleration over time is equal to d over dt of our velocity, 0.3 t cubed minus 3t squared plus 8t. So if I take the derivative of that, I get 3 times 0.3, which is 0.9 t squared, remembering our power rule, minus 6t plus 8 as our acceleration function. And so to go the opposite way, we have the fact that velocity is the derivative of position. So if we go the opposite way from derivative, what do we get? An integral. So this can go to x is equal to integral of v of t with respect to time, of course. So now let's do this. Here we're going to get that x of t is equal to the integral of 0.3 t cubed minus 3 t squared plus 8t dt. And so that's going to equal, if we remember our power rule, 0.3 over 4 t to the fourth minus t cubed, since we have 3 over 3 there, plus 4t squared. And of course we have the plus c constant, we can't forget about that. The good news is they give us an initial condition, that x of 0 is equal to 0. So x of 0 is going to be equal to 0 minus 0 plus 0 plus c. So we know that c has to equal 0 because that's all equal to 0. Okay, so x of t is now equal to 0.3 over 4 t to the fourth minus t cubed plus 4t squared. And so now we just need delta x. So we need to look at the time that they give us from t is equal to 0 to t is equal to 6. So they already told us that x of 0 is equal to 0. So all we need to do here to find delta x is to plug in x at 6 seconds, which, if we come down here, running out of space, that's just going to be equal to 0.3 over 4, 6 to the fourth, minus 6 cubed, plus 4 times 36, which is 6 squared. And so that should all be equal to 25.2 meters, which is equal to delta x. And so there you go. Using our relations for position, velocity, and acceleration, we got these three answers. So, moving on, we now have a problem to do with springs. So it gives us the module of the energy of the spring, which is equal to k ln x, where k is a constant, and there is a weight on the spring. So we have to find the units of k and the distance stretched. So already we're thinking units of k, I know those, that's newtons per meters. Well, unfortunately this is wrong because that applies to Hooke's law. And in this case, our energy does not obey Hooke's law. You can actually have springs which are non-Hooke law springs. They don't obey F is equal to negative kx. They don't obey that the energy is equal to half kx squared. So in this case, we've got to use calculus to find out what's going on. So we can use the relation that the force of x on this spring is going to be equal to the negative derivative of the energy with respect to x. And of course, that's going to help us a lot. So if we take negative d over dx of k ln of x, we know that k is a constant, so that's fine, that can come out. And the derivative of ln x is 1 over x. So here we're going to get negative k over x. I just took the derivative there. And so first of all, we can find out what the units of x are if this is equal to the force. So let's put the equation in terms of units. So k over meters is equal to newtons. And I'll specify units here. And so k units are equal to newtons times meters. Remember, k is a constant. We can set the units arbitrary to what we want to help us with the problem. So this is the first part of the problem. So the next part is the distance stretched. So it's still a spring that obeys Newton's laws, just not Hooke's laws. And so in equilibrium position, the sum of all forces should be equal to 0. So the only force on the spring, aside from the spring itself, is this 100 newtons down, so minus. And then we have the spring force itself, which is the only other force in the problem. So that will be equal to k over x. And that's all equal to 0. So now all we've got to do is solve the problem for x. So I'll take 100 over and divide by k. So x is equal to wait, let me redo this, sorry. So k over x is equal to 100 newtons. So x is equal to k over 100 newtons. And k they give us here is 50. We can write these units in now. And so this is equal to 50 newtons times meters over 100 newtons. You can see the units cancel out for something we want, and we get 0.5 meters as the distance traveled. So again, another application of calculus in physics. And so the last example we will do is how to go from force to work done. So we know that work done is the change in energy, which means that when we use our relation F is equal to negative du over dx, d means change. So that means that work done is actually the integral of force over a specific distance. So we have this relation here for our force, and it says they want to find the work done for the time where F is greater than 0. So first we have to find where it's greater than 0. So we need to find when 5 plus 4x minus x squared is equal to 0. And so we can factor this into x plus 1 x minus 5 is equal to 0, which means x is equal to minus 1 and 5. So now we know that, we can go and put our bounds in the integral, minus 1 to 5 of 5 plus 4x minus x squared dx, of course. And so now all that's left is to evaluate this integral, and so we're going to get 5x plus 2x squared minus 1/3 x cubed from negative 1 to 5. And if we plug in the 5 to there and minus 1 there, we plug those in, we should get that this integral, which is the work done, is equal to 36.7 joules. So I hope this video helped with some methods of calculus we can apply to physics in different scenarios. And I will catch you in the next video. Have a wonderful day.